Hello and welcome everyone, wherever you are in the world, to this talk on document artificial intelligence called a unified CV, OCR, and NLP approach for scalable document understanding. And my name is Patrick Buchma. I'm speaking today from Seattle, Washington, where I'm a machine learning engineer at DocuSign. I'll be speaking alongside Misha Chertushkin, who's a senior data scientist at John Snow Labs. So we're really excited to share with you some of the work we've done in the field of document AI. And before we get started, I just want to orient everyone with an outline of what we're going to cover today. So we'll start out by outlining the specific problem within document AI that we're interested in solving. And we'll cover a little bit of the previous research that's been done in the field and how this research relates to what we're working on. We'll next talk about our solution, which involves a hybrid approach combining computer vision, optical character recognition, and natural language processing. And we'll talk about the data set that we needed to acquire and build the infrastructure for in order to build these models. Next, I'll hand it over to Misha, who's going to walk us through some of the basic neural net architectures that we've chosen and work well for this task. And then he's going to hand it back over to me, and I'll close with some conclusions, lessons learned from rolling out this machine learning solution and some of our future work. Just a quick disclaimer, this project is currently pre-GA, so we've omitted some of the details. We've done our best to include what we think is the most interesting and relevant material on the machine learning models, but please feel free to ask questions if we don't cover something that is of interest to you. So unstructured text is the largest source of human-generated information, and it's growing at a very rapid rate. So documents are part of this growing source of digital information, of unstructured text. At the same time, the world is increasingly moving to a digital-based means of communication, and paper is getting phased out. Therefore, there's a growing need for organizing this incredible amount of information. And that is where document artificial intelligence comes in. We want to make it as easy as possible to navigate and interface with digital documents so that we can save time and free it up to do some more interesting things. So you can imagine the complexity of documents is very wide. Everything from a simple one-page invoice or receipt all the way up to 100-page contracts. And what we want to do is automate the extraction of structured information from all of these types of forms. So you can appreciate that there's a high and growing variation in the layout and the format of how this information is presented. For me, this is kind of an ideal machine learning problem in the sense that it's tractable. And in addition, unlike a lot of AI, it's actually useful, right? The solution is useful to many people. On a personal level, it's also been a really interesting problem to work on because it hasn't been solved before, but it is also solvable. So to start, just consider this passport application that you see on the screen, and imagine you want to automatically fill out all the information that you're supposed to on this page. So you have to fill out your name, your social security number, your address, and we want to do this in an automated way. So what we're aiming for is shown on the right, where we've automatically inferred what exactly you're supposed to fill out and where you're supposed to fill out that information. So document AI is a small but growing field, and to situate this problem within the broader context, I want to go over some of the previous research that's been done that is most closely related to this work. One of the most commonly studied areas is the automated extraction or parsing of invoices and receipts. So that involves you taking a receipt, you scan it, you figure out, what is the total amount, what is the, what is the address maybe, things like that. In this problem, you need to harness both textual and visual information. So typically this involves some kind of combination of computer vision and text classification or natural language processing. So there's been a couple different approaches recently that have basically combined this textual and visual information. Liu et al. Proposed a graph convolution technique, treating the document information as a graph combined with the textual information. There's also been Chargrid and Berggrid, both approaches that take the textual information and together combine it with the actual physical locations of the characters on the page. And most recently, Google Brain came out with a kind of a neighborhood-based approach, which involved learning a neighborhood embedding of the words, the target words kind of in an NER context, and using those as features in a broader neural network. So there's a couple factors that distinguish our work from this pre-existing research. So first, these approaches work well at extracting, say, the total amount on a receipt, but it's unclear how they perform when you scale up from an invoice or a receipt to just an arbitrary layout. And we are interested in solving this problem for any type of layout, any type of form, any type of document. And then the second major distinguishing factor is that the information or the documents that we're interested in parsing, they don't actually have filled out information. So the information is blank, and effectively we're trying to determine what actually goes where. So in general, it's a similar problem, but obviously the approach has needed to be quite different because the information is organized in a very different way. In general, the research is at an early stage, I would say, in document AI, but I think we all expect it to increase rapidly as the world is moving increasingly digital. So the solution that we've come up with to solve this problem, again, involves a hybrid approach combining computer vision, OCR, and NLP. And first, just consider the fact that humans create documents in whatever format best suits their immediate needs. They can organize information however they want, and they can prepare documents however they want and send them in to get that information back. So really, we need to solve this problem at a general level. We want to learn kind of abstract the representations of how information is organized on these pages. So the ideal solution is really to learn these high-level representations the same way, is to learn these high-level representations with AI. We don't find that rules-based engines like template-based or position-based work very well because they require the information to be organized in a specific way. And so these are not going to scale. Now, I mentioned that this is a kind of an ideal machine learning problem, but it is far from a textbook application. And one of the big reasons for this is the data. There is no data set that you can just download, from Kaggle and start training models. There are some invoice data sets that I mentioned earlier, but they do not apply to this specific problem because, again, the information is already filled out. So we require building the data set from scratch. And unlike a lot of tech companies, we don't actually use our customers' data to train machine learning models. So we had to build this data set ourselves. Fortunately for us, we have a very talented data scientist on the team named Michael Palazzolo, and he basically came up with a way to mine the internet and build this data set that we needed, build the foundation of the data that we needed, that we then used human labeling to really take it to the next level, take it to make it really high quality. So the data set was first acquired by mining the internet, and then it was the labels were annotated precisely and with extensive iteration with human-in-the-loop quality assurance. We also used a technique from perceptual hashing to ensure that the document images themselves were different and that we had sufficiently high variation and that there was no sort of bleeding between the splits, between the training and validation splits, to ensure that we had, you know, a high quality sort of a pipeline for training the models. We've also built the infrastructure for this model building so that we can support on-the-fly model and for on-the-fly record creation for near real-time experimentation. It's deep learning framework agnostic. And right now we have about 200,000 weekly labeled documents. These are from automatic annotations. And then we have just over 10,000 perfectly labeled documents from the human-in-the-loop QA. Now, I should note that only publicly available non-customer data was used to build this database and to train the models. Next, I want to hand it over to Misha, who's going to cover the neural net architectures of the computer vision, OCR, and NLP parts of the model.
Thank you very much. Okay, so our pipeline, which we created, consists of 3 parts. Starting with computer vision, it is important to mention that from the computer vision point of view, this is a classical object detection task. When we have some document as an input, and we need to predict bounding box and the class label as an output. So on this slide, you see that we have unlabeled document to the left, and the goal is to predict bounding boxes with 4 coordinates and class label. Sometimes it is just 4 coordinates, x0, y0, and x1, y1, and sometimes it is x0, y0, and width and height. We had identified several complexities, which will be presented in the next slide. So there are several complexities that we needed to solve. For example, we had size variation. Our bounding boxes could be very small or they could be very large. Also, it is important to mention that these objects could be densely packed inside images, or they could be relatively sparse. And imagine a document that have a table, and this table consists of a lot of bounding boxes. So this was another challenge. Also, bounding boxes that we wanted to identify had different aspect ratios. Sometimes they were squares, sometimes they were rectangles. For checkboxes, they were perfect squares, and so on. And another complexity that we needed to solve from the computer vision perspective was that these bounding boxes, they were dependent on long contextual dependencies. The signal indicator for example, signature bounding box could be something in the top of the document, and we also needed to identify it correctly. So, and on the next slide, we decided to try several experimentations. We started with SSDs. This is the simplest model in object detection world of machine learning, single shot detector. This model does not have region proposal network as other object detectors. Instead, this model just produces default boxes for the network, and then with the regression loss, these default boxes are shrinked to the actual predictions. We decided to use this model because it is very fast, and it was very easy to try it in the first place. And it is, and we also saw the evidence that these models are really fast. SSDs are very good when you have constraints for inference time, but from the accuracy, from the performance perspective, they were not very good. So we decided to move to another realm of families. And on the next slide, we decided to move to models that utilize region proposal networks. Region proposal networks work in the following way. At first, they try to predict some class agnostic bounding boxes, and they backpropagate through these predictions. And then on the next layer, they try to do the same job as SSDs to shrink these bounding boxes to the actual prediction classes. So we can even say that in SSD, the task of region proposal network is fulfilled with default boxes. We also decided to use a rather complex family of algorithms inside region proposal networks, which is called faster RCNN, and even more, we added two distinct features to this faster RCNN model. We added inception block and we added resnet block. Inception block allowed us to make a network wide, and the model could learn the dependencies in best relevant way for it. And residual block, resnet block, allowed us to make network deep, because when network has residual connections, it can use them as skip connections and backpropagate the signal without gradient decay. So this was about first part of our pipeline, and the second part of pipeline is OCR. OCR works as follows. We take all our bounding boxes that we identified with computer vision, and then we take the coordinates, and then we predict the word. We recognize the words with OCR engine. For this task, we used custom service, custom build of Tesseract, and we tuned it for speed and accuracy. And after we have coordinates and we have words, we can go to the third part of our pipeline, which is NLP. And in NLP part of pipeline, we perform basic classification task. So we take all our words that we identified with locations and with OCR, and then we use bidirectional LSTM together with custom embeddings to predict, to solve the classification task. So this NLP part of the pipeline just assigns some class label to the predicted bounding box and corrects it if there is any need to that. So and then I pass the words to Patrick. Okay.
Thanks, Misha. So you just saw this hybrid approach that combines CV, OCR, and NLP, and ultimately from this set of models, we get the locations and what information is supposed to be entered at the specific location on an arbitrary form and with an arbitrary layout. One of the challenges here is how do we measure end-to-end performance? So because it's a combination of CV and NLP, we do use a hybrid scoring metric that combines kind of traditional measures like MAP and an F1, but that doesn't get us all of the way there. And you know, you can imagine that the user doesn't really care what, you know, the mean average precision is across, you know, 0.5 IOU to 0.95 IOU, right? So what we've attempted to do is to match what we think humans care about using sort of the combination of these metrics in a specific way, such that we can score the model in the way that we think a human would interact with the document. So this involves rather extensive testing on a diverse of a data set as possible. I mentioned at the beginning that we don't use customer data to train the models. So that also means that we have to do our validation outside of that black box. So that means that we require a very large and diverse data set so that we can accurately capture sort of the nuances of how these models perform across, you know, many different types of documents, highly diverse documents. So just a quick recap how this works. So again, we start with a document image. So just image bytes that we feed into the computer vision model, then OCR, then NLP. We get the locations, we get the type classification for all of the bounding boxes that have been recognized by CV. And we score the model with a hybrid sort of CV NLP based approach. And then we iterate. And of course, we do this many times. We retrain the computer vision models, retrain the NLP models, and often require going back to the original data and relabeling according to what errors we're seeing in the final product, in the final output. So I'll close with some conclusions and future work. These are kind of some lessons learned from our experience with this kind of novel ML problem. Document understanding in general, we think is really well suited to an AI-based solution. We think that deep learning works well at learning sort of high-level representations within documents, and similar to the way that a human might be learning these representations. It's very clear that if you want to build highly performant models, you need very, very high quality data. Of course, you can get some of the way there with imperfectly labeled data, but if you're really trying to reach sort of human level performance on this task, then you need almost perfectly labeled data, or as close to perfect as you can get. And that really does require extensive human in the loop data set curation. And fortunately, we've been able to move towards that quality of a data set over time. One interesting aspect that we learned, I think, from the computer vision side of things is that state-of-the-art computer vision models are or can be adapted to what is essentially negative space object detection. So we have we're basically just labeling blank space on a page, but with sufficiently deep networks, you can learn sort of the context surrounding that blank space and what matters in terms of what you're actually supposed to fill out. So that was kind of an interesting feature that we saw from these computer vision models that worked well for this task. Speed accuracy trade-offs are always going to be critical factors at every stage of development, and that means sometimes that we're going to use perhaps a network that's twice as fast at the expense of some tiny decrease in performance. So that's always kind of something that we kept in the back of our minds as we're building these models. How fast they are and how fast they are relative to the speed, how fast they are relative to the performance increase that you're getting. And finally, I think one of the most important lessons we learned is that when you're designing a novel ML solution, it's extremely valuable to consider how humans are performing the task and attempt to emulate that with the machine learning models. So that is what we've attempted to do, and we're really excited about some of the results so far, and we're looking forward to the future. So thank you very much. I'll close just with acknowledging the agreement intelligence team at DocuSign. So Matt Braun, Michael Palazzolo, Roshan, Satish, Vincent Young, and Nathaniel Wickman. They have all done incredible work in this space and really made this possible. And finally, I'd like to thank the John Snow Labs team, David Talby, Anju, and Vaisal for helping us with some of the earlier prototypes, and in addition for giving us the opportunity to present at this talk. So thank you very much.